Next lesson in Chapter 3, we'll talk about measures of relative standing. In particular, we will discuss something you have seen in integrated algebra. We will also discuss something that brings it to the college level in z-scores. Z-scores, sometimes called a standardized value, is the number of standard deviations that a given value is above or below the mean. It's an exact score, and basically it tells us exactly how far away the particular data value is from the mean. The formulas for calculating z-scores for a sample, it is x minus the mean, x being the data value, of course, divided by the standard deviation. And for a population z-score, we have x subtracting the mean of the population over the population standard deviation. The round-off rule for z-scores is always going to be 2 decimal places. We always round to 2 decimal places in the case of any z-score. Interpreting z-scores is relatively easy to do. Z-scores can either be positive or negative. If the z-score is positive, it means it's above the mean. If it's negative, obviously it means then it's below the mean. We've talked about what usual values mean, and usual values are any data value in the data set that is within 2 standard deviations of the mean. So usual values will have a z-score between -2, or 2 standard deviations below the mean, and +2, or 2 standard deviations above the mean. If the z-score is less than -2 or greater than 2, then the value becomes an unusual value in the data set. Let's take a look at an example here. Sample results from a group of men at a modeling agency reveal that the mean weight is 172 and 55/100ths of a pound. The standard deviation in this case is 26 and 33/100ths of a pound. We want to find the z-score for the man that weighs 237 and 1/10 pounds. Pause the video at this point to give yourself a chance to do it on your own. So right away we have sample results, so we're going to be using the sample formula for z-scores. And what I've done is I took x, which is the data value, and I subtracted the mean, and then I divided it by the standard deviation, and I rounded to 2 decimal places, and I get 2.45. This also means that the man's weight was an unusual value at the modeling agency. Finding percentiles are a key source of data, and the percentile is a measure of the numerical location of data. You're all used to percentiles, especially with test scores. Those of you that are seniors are probably finding out what percentile you are in terms of your class and in terms of your SAT scores. Right from birth, you were put into percentiles with your height and weight. Percentiles are typically noted with subscripts. The example I have there is P sub 60 would mean the 60th percentile. Your data values must be in order to find percentiles. It's important that they are in numerical order. The percentile formula that we're going to talk about here is where k is the percentile, n is the values in the number of values in the data set, and x is the actual data value. So what we have here is p sub k of x equals the number of values that are less than x divided by n, which is the total number of values in the data set, times 100. Finding data values given a percentile becomes slightly more difficult, and we have to use a different formula. We call that formula the locator formula. And the locator formula allows us to find data values that correspond to a given percentile. The locator formula in this case, L would be the position of the value, K again is the percentile, and N is still the number of values in the data set. So L is equal to K divided by 100 times N. If you look at the percentile formula, it's just a reformation of the percentile formula. Once the location's been found, we have two situations that could possibly occur. If the L value is non-integer or a decimal, you want to round up to the next value. It does not matter what the decimal is. As soon as you get a decimal, you want to round up. It could be 21.00001 and you want to round up to 22. You see my example there. If L is 21.12, you want to use the 22nd value. That's the locator. It could also be a whole number. If the value of L is a whole number, we want to take the average of that particular placement plus the placement to the right of it. Example, if we got L equal to 23, we want to use the average of the 23rd and 24th value. We're going to do three examples with the same chart that you see on the left here. This is movie budget amounts, and it's measured in millions of dollars. We have 35 different scores, and what we want to do to start is we want to find the percentile for the value of 29 million. So what we do to start is we're going to use the percentile formula, and we have P sub k of 29. 29 is the data value, and there are 6 values that are below 29. We have 4.5, 5, 6.5, 7, 20, and 20. So 6 over 35 times 100, rounded off to the nearest whole number, as we always do for percentiles, is 17. So therefore we come up with the conclusion that 29 million is the 17th percentile. Let's use the same chart for finding a given percentile. This time I want to find the value of the 90th percentile. In this case, I'm going to be using the locator formula. So L would be equal to, in this case, 90 over 100 times 35. When I do the arithmetic, I get 31.5. If I have 31.5, I want to be rounding it up to 32. That means I want to use the 32nd value out of my 35 values in the data set. That means the 32nd value in the data, if I count up from the smallest to the largest, is 150 million. Therefore, the 90th percentile, or P sub 90, is equal to $150 million. Let's do an example where possibly the locator formula comes up as a whole integer. If I find the value of the 60th percentile, I take the locator formula again, doing 60 over 100 times 35, and it gives me a whole integer answer of 21. Because I have that whole integer answer, we average the 21st and 22nd values. In this case of our data, we have 70 and 72 million respectively. So I want to average 70 and 72 million. Therefore, the 60th percentile of the data is $71 million. Your homework to start this section is textbook pages 126 and 127, numbers 1 and 2, and 5 through 17 odd.